My name is Joe Schwab, and I co-direct the Center for Surgical Innovation and Engineering at Cedars Sinai in Los Angeles, and happy to speak about AI-driven multimodal wearable devices. Full disclosure, the devices that I'm presenting tonight, I hold a patent on all of these devices. So our lab at CSIE, we take advantage of classical physics and engineering as well as machine learning, and we use several modalities in our wearables, including acoustics. So we're talking about a sound that is a different frequency than ultrasound, lower frequency. So it's not something we're using for visualization. We use electrical signals, and we also use optical systems. And what we're trying to do is to conceptualize, to build, test our wearable devices and bring them to the clinic. And so our lab is mostly made of engineers. I'm not an engineer, but everyone else in my lab is. And that's how we're able to build a lot of these different devices. And ultimately, we're trying to expand our understanding of physiology and therefore pathophysiology. So when we think of multimodal wearables, really the neuromuscular system is quite complex, as everyone here knows, and so you really need a multimodal assessment, just like with driverless cars, right? I know in several cities and certainly in LA, there's a lot of there are Waymos everywhere here, and that the Waymo, for instance, is using multimodal devices such as radar and lidar. They have multiple cameras, obviously. And they're also using audio, and all these are being analyzed in real time. I would argue that medical decision-making can be more complex than driving a car, but yet the car industry is much further ahead of us in this regard. And there are many mobile wearables that are available. I think everyone here probably has some sort of a smartphone or a watch, smartwatch, or a ring. And these are what we call type 1 wearables. And in this case, the mode of the wearable device and the signals are completely independent. And whereas our lab is really working in type 2 and type 3 wearable devices, in this case, the modes may be different, but the signals are dependent upon one another. So we have devices where the electrical signal that our device is interpreting is predicated on the acoustic signal, for instance. And the more advanced devices are where the mode and the signals are interdependent. An example of that would be you're using an acoustic energy to change the electrochemical makeup of tissue, and therefore the signals following up. That's what I mean by multimodal and type 3 devices. So this is just an example of one of our devices, the electroacoustic wearable. And if you look on the right side of the screen, you see that there are multiple transducers, and this is just a mock-up of one of the devices around the patient's calf. And the transducers can send, again, either acoustic or electrical signals. And the transducers can also behave as sensors. So the idea is you send an acoustic wave at a certain frequency through the tissues, and then you measure those acoustic waves after they've passed through the tissues, and they can give you a lot of information about the tissue. So some of our studies have shown that we can non-invasively assess tendon health and mechanical properties of tendons. We can detect injuries, both in tendons but also in muscle. We can detect contraction speed, contraction amplitude, and we can even do nerve conduction velocity with these wearables, all non-invasively. And so the idea here is that you can gain a huge amount of information from these types of devices. One of the big constraints that we face now is the amount of data that we're generating. So all of our devices currently are wired. They're wired because we don't really know what signals are important. And so we're collecting huge amounts of data, and then we have to parse through that data to find out what signals are important, so that we can then just collect that data, and then that allows us to have a wireless device. We're not quite there yet with regard to that. Another device that we've developed takes advantage of something called frustrated total internal reflection. And so this is how fiber optic cables work. And if you look at the image in the upper right, you can see this beam of light that looks like it's trapped within this tube of glass. And in fact, it is trapped. And what's happening is as the photons are traveling, they create an electromagnetic field. And the electromagnetic field traps the photons in that glass. If you disrupt the electromagnetic field, then the photons can escape, and the photons would leave the glass. And so if you look at the figure in the lower left of your screen, that's our plantar pressure device. And so here again, we're sending photons through the pane of glass. And if you look down at the glass, you don't see any light. And again, that's because the photons are trapped by the electromagnetic field. But if you were to disrupt that field by stepping on the glass, you get a high resolution pressure image of the feet, similar to what you see in the middle there. It also gives you a very high resolution assessment of the surface roughness, which I can talk about later. But so what do I mean by high resolution? So many of you are probably used to looking at force plates, right? So force plates are used quite a bit in assessing patients. But if you want to, say, look at the Mona Lisa and you're using a force plate, typical force plate, you're going to have four sensors. And so if you're looking at the Mona Lisa, this is what you see on the left. Whereas in our device, you're only limited by the number of pixels in your camera. And so you can get an extremely high resolution image. And that turns out that matters for lots of different reasons. One of the things that we have become interested in is balance, right? And so one aspect of balance is just as it pertains to fall risk. And we started wondering whether or not we could help predict who's going to fall and therefore prevent them from falling. And so we use a lot of the CDC's criteria. CDC has a screening test that pretty much all of you, if you've been a patient, you've been asked, or your patients have been asked. And it's an assessment of their fall risk. Do you have a fear of falling? Have you fallen? There's usually several questions. And what happens is they get binned into high fall risk or low fall risk. The CDC also recommends for balancing what's called a 4-stage balance test. So if you look at the lower left, again, you've got four poses. The first pose on the far left is just a neutral pose, something you might stand when you're being weighed. And then the poses get gradually more difficult until you see the one on the right, where you're standing on one foot. The thing about most of these tests, like the 4-stage balance test or the timed up and go, for instance, they're really just timed. All those, the only data that you're collecting on those tests is how much time, how long these patients were able to maintain these poses. Whereas we're trying to add a lot more nuance to that by providing more data about their sway, for instance, but also looking at their muscle engagement. So the image on the right, you can see a subject standing on the pressure plate, and they have this electroacoustic cuff around their calf. And so in this case, as I said, there's a lot of data that we're collecting, but we're just looking specifically at their sway, for instance, and looking at their muscle activity. And so if you look just at sway alone, not surprisingly, as the difficulty of the pose increases, the sway increases, right? The variance in their sway increases quite a bit. What we found that was interesting was if you look at there are red dots. Those red dots are indicative of subjects who failed the CDC screening criteria. So these patients were deemed to be high risk of fall. And we only had, I think, 8 patients out of this group. I think there were 80 patients in this total. 8 patients in this particular group who failed the CDC screening test. So they would be in this group of patients who might fall. But if you notice that they're all at the near the outside of our measurement in terms of what's our normal range, what's our average and standard deviation. So even with the standard pose, just standing there for 30 seconds. We think we can detect a signal that might indicate someone who's at risk for fall. And so you can imagine how this would be useful in terms of assessing, screening patients. They're coming in. You can use this for weighing someone and assessing their fall risk. We have studies looking at cervical myelopathy, for instance, and looking at as an outcome for patients. There's a lot of different things you can use this for, but just as an example. In the same group of patients, again, the same set of tests, here we're looking at the electroacoustic cuff, and specifically we're using the acoustic energy. And what we're looking here is, again, the changes in the variance of their amplitude of their muscle signal. So it's a relatively crude use of the data. But here again, you can see that you are able to detect which patients are failing the screening test from the CDC, just looking at their muscle engagement. And if you think about it, what's happening when you're a young, healthy person or an athlete, they have actually a normal cadence to their sway, and they have a certain level of engagement of their muscles. Whereas in older patients, you actually get much less of that. They're much stiffer, and they tend to have a little bit less of a normal cadence. It's much more of a stiff cadence, and that I think is one of the reasons why they're falling. We're also finding that the patients have much more muscle engagement in their proximal muscles in their thighs and less so in their calves, probably because they're not reacting to their instability until they get so far out of balance that their proximal muscles, like their thigh muscles, become engaged. And so there's a lot we're learning from about balance and how people maintain balance with these devices. Another application that we're doing is looking at patients who've had an EOS film and looking at the center of gravity from our pressure plate relative to your SVA, for instance. And so anyway, there are a lot of different applications that we're exploring with these devices, trying to understand a little bit better about what's happening truly physiologically with our patients. So in conclusion, I feel strongly that AI-driven multimodal wearables can be extremely helpful. It is time consuming. It's difficult to build these and to assess the data, frankly. But I do think that they're going to make a difference in our understanding of physiology and therefore pathophysiology and hopefully in medicine. Thanks very much.